Hello everyone, my name is Elena Wiggins and this is my mini lecture for Organic Chemistry 211. I'm going to explain the Williamson ether synthesis from chapter 18, section 18.2. The goal of this reaction is to make an ether which has a general structure of ROR'. The key equation is an alkoxide ion reacting with a primary aldehyde to form an ether or hydride ion. Before looking at a reaction, it helps to know what an ether actually is. An ether has an oxygen atom between two carbon groups. It is similar to an alcohol in shape, but it does not have an OH bond. In chapter 18, ethers are described as relatively unreactive compounds, which is one of the reasons they are often useful as solvents. For today, the important point is that making an ether means forming a new carbon-oxygen bond. The Williamson ether synthesis makes the carbon-oxygen bond into two main parts. First, an alcohol is converted into an alkoxide using a strong base, such as sodium hydride. The alkoxide is important because oxygen has a negative charge, making it a strong nucleophile. The second alkoxide reacts with a primary aldehyde. The alkoxide attacks the carbon attached to the leaving group. The ether product forms. The mechanism is SN2, meaning it happens in one step. In the example shown here, the methoxane attacks bromoethane. The oxygen uses an electron pair to attack the carbon attached to the bromine. At the same time, the carbon-bromine bond breaks. The bromine leaves, meaning the final product is methyl oxidane. The important thing here to remember is the new carbon-oxygen bond as the leaving group leaves. The aldehyde should be primary because SN2 reactions need a backside attack. A primary carbon is less crowded, so the alkoxide can reach it more easily. A tertiary aldehyde is too crowded for the SN2 and is more likely to react by elimination instead. So, when planning a Williamson ether synthesis, the aldehyde should usually be placed on the less hindered side of the ether. Now, let's solve a practice problem. Suppose the target molecule is a methylpropene ether, written as shown on screen. First, identify the ether bond and mentally break one carbon-oxygen bond. A good plan is to use sodium methoxide as an alkoxide and one bromopane as the aldehyde. This works because one bromopane is primary, so it's good for SN2. Methoxane attacks the carbon bonded to bromide. Bromide leaves the methyl propyl ether forms. To summarize, Williamson ether synthesis uses alkoxide plus a primary